Welcome to our discussion on modeling uncategorized problems. In other words, we're going to look at how we can solve some of the more unique word problems that you might come across. So first of all, there are kind of the basic 4 steps. These are called POYAs, steps for solving any kind of problem, right? Word problem, life problem, whatever, right? And they're pretty generic steps. I mean, step 1, understanding the problem. Step 2, devising the plan. Step 3, carry out the plan. And step 4, look back. You can't get more generic than that, right? So, as an overarching idea, it's helpful, but in an application sense, it might be a little bit too basic. So what I've done is I've taken those steps and I've kind of given you a little bit more detail, put a little bit more meat on the bones of how you can apply those 4 concepts to the types of word problems, mathematical questions, and things that you'll come across in most classes. So instead of understanding the problem, well, in terms of understanding the problem, that means you really need to read it all the way through. So the first time you come across a word problem, you want to read it all the way through and just look for a sense of the theme, right? Is it talking about objects moving in different directions? Is it describing a geometric figure? Is it involving mixtures? Is it involving money? What's the theme? Because different themes have kind of different specific tools to help you solve them. So if you can get that theme figured out, it really helps. While you're getting that idea of the theme, it's always a good idea to identify the question and label the unknown. Somewhere in that word problem is going to say, what is blank? What is blank? How much of this, right? It's going to be some sort of question. And that's going to be your unknown. That's going to be your X or whatever variable you want to use. I often tell my students, stop using X all the time and pick a letter that denotes what you're looking for, right? If you're looking for the price of something, use P. If you're looking for the volume of something, use V, those types of things. But you want to identify that question and label that unknown. And then if you can, draw some sort of simple picture or diagram. If it's talking about objects moving, then draw some lines and little arrows and show in what direction things are moving. If it's describing a geometric shape like a rectangle or a triangle, then draw a rectangle or a triangle, right? Whatever you can to give yourself a little picture helps, because we're visual creatures and we learn and understand more with our eyes, with pictures, than with our ears, with sounds and words and stuff. All right, so once you've done that, step 2, devising the plan, really means go back, reread it in small pieces, and write down everything it tells you. So you're taking it in little chunks. Blah, 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 blah is 25 feet. You stop, and then on your little picture, you write down 25 feet. And then blah, 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 blah is 35 feet. You stop, you write down that. So, blah, blah, blah is 2 times as long as this. Okay, and then you go, okay, this is 2 times. So you take each little piece of information and translate it and write it down, label things on your picture, fill in a table or chart, whatever you're using to help you solve that. You're going through all of those bits and pieces one at a time. Once you've done that, you need to look back at all the information you have, right? You've written everything down, and everything's labeled, it's all there on the paper. And somewhere in there, the solve it part that they talk for part 3 is you have to find the hidden equation. Somewhere in all that information, something is related to something else. Either they've specifically said this is equal to twice of this, or this is 10% more than that, or they've given you 3 sides of a right triangle and you go, oh, they gave you 2 and you're trying to solve for the third, and you remember, oh yeah, Pythagoras' theorem relates the 2 side, the square of the 2 sides to the other. So when you look at all that information, you look at your picture, you figure out all the stuff that you have, somewhere in there is a hidden equation, whether it's translating the English or it's thinking of properties and rules and things that relates all that information, right? You're going to have a bunch of numbers and you're going to have a variable, and somehow you got to throw all that stuff into one or more equations. Hopefully you only have one, because it's a lot easier to solve just one. But even if you're writing down multiple equations, that's fine, because then you do some work to take multiple equations and translate them and work them, and pretty soon you'll get them down to one equation. Then you'll solve that one equation and kind of work backwards from there. And then after you've done all that, the last step is to check your work, right? Double check all your steps, make sure you haven't made any simple math mistakes. Always make sure that your answers make sense. Are they roughly on the right scale? If they're talking about sides of a triangle and one was 25 centimeters, the other one was 35 centimeters, and you get an answer of 4,000 centimeters, you're like, okay, that doesn't sound right. Things like that. If you have a question that's involving money or time and you get two answers and one of them is positive and one of them is negative, you can't really have negative time. You can't really have negative money. I mean, you can technically owe money, but usually in the context of the question, you can't have negative money. If X represents the number of things produced, the number of shirts you sell or the number of widgets you build or whatever, again, you get two answers and one of them is positive and one of them is negative. The negative one just doesn't make sense, so you throw those away. So that's kind of the step 4 double checking stuff, right? Okay, now those steps can pretty much help you through just about every problem out there. Now the next couple examples I'm going to show you are really weird ones where sometimes you can't even draw a good picture. But I have other videos out there that walk you through more of the standard things where you're dealing with money and percents and mixtures and time and work and distances, and all those things can be done really well with these simple 4 steps, these guidelines you see here. Okay, let's look at our first example. And this is a very typical question, actually. You get these a lot in math classes where you have an object, a pool or whatever, is being filled at a certain rate, and then at the same time it's being emptied at another rate, and then you have to figure out how long it takes until the whole thing is full or the whole thing is empty, depending on the rates of the two things. In this case, we have a swimming pool that it can be filled, right? There's an inlet pipe that can fill that entire swimming pool in 24 hours. And then there's a drain pipe that can empty the same pool in 30 hours. And then here's the scenario. The pool is half full, and then the drain pipe is accidentally opened, and they want to know how long will it take for the pool to fill. Well, first of all, you got to ask yourself, is it even possible? Does it drain faster than it fills, or does it fill faster than it drains? Because if it drains faster, it'll never get full. But if it fills faster, then it will get full. And yeah, it does, because it only takes 24 hours to fill, but it takes 30 hours to drain. So it fills faster. Okay, draw a picture if you can. Now, of course, it doesn't have to be this fancy, but just give yourself a little box with a little inlet pipe and a little outlet pipe. And on the inlet pipe, you can label, 24 hours. And on the outlet pipe, you can label 30 hours, just so you understand what's going on. Now, we've already talked about, will this happen? Yes, there is a solution because it's filling faster than it's draining. So that's good. It's always good to kind of check and make sure that everything makes sense. Now, let's see if we can figure out how to solve this. Let's devise this plan. And we know that if we're trying to fill something, we're basically trying to complete a job. And that one job is filling the pool. And that is done with certain work, right? We have the work that's done by the inlet pipe, we have the work that's done by the drain pipe. And obviously, the job is completed when you take the inlet pipe and subtract the drain pipe, right? Because the drain pipe is working against us. So that's why we've got the work of the inlet minus the work of the drain gives us one job completed. But wait, is this correct? We've already have half the pool full. So we can actually make our life easier by kind of simplifying the question. And one of Polya's suggestions is to always work a simpler problem. Polya, like I said, is the person who came up with the generic 4 steps. And since the pool is half full, we're really only trying to figure out how long it takes to fill the other half of the pool, knowing that if it takes 24 hours to fill the pool, it took 12 hours to fill the first half. So we've already spent 12 hours, and now we're just trying to figure out how long it takes to do the second half of the pool. Well, just like distance equals rate times time, right? That's a pretty simple one. We all know distance equals rate times time. Well, guess what? Work equals rate times time as well. This is another example of a similar problem, and it's really easy to solve, right? For one of these, if we have 2 of them. So we're trying to figure out how much time it's going to take to fill half the pool, and that's the work, right? Half the pool, if we know the rate. And we do know the rate. The rate is how fast it fills minus how fast it empties. Well, oftentimes you can figure out a rate by just doing this kind of simple math, that the work equals rate times time. So the rate basically equals work divided by time. So the one, job filling one pool divided by the 24 hours it takes, and that tells you that the time to fill, or sorry, the rate at which it fills is 1/24th. And we all, time is always constant here. It takes the same time because, we start a stopwatch and it goes. That's what I mean by time to fill equals time to drain. It means those two things are running at the same time. And if you ever have a question where that's not the case, like something is turned on and then something is turned on later, like this one where the inlet pipe was turned on and then later the outlet pipe was turned on. Do you see how we reset it and made time the same by just going, well, that first 12 hours just happened and now the clock is going to start once we open the other inlet, right? Or the outlet, if you want to think of it. So we can do the same thing and figure out the work done by the drain, and that's 1/30th because it takes 30 hours. And then, of course, we're trying to complete a job, but in this case, a job isn't one thing, it's 1/2. So 1/24 minus 1/30, that's the two rates. If we can figure out that rate, then it's going to be that rate times the time that we're looking for equals 1/2. Right? So we're basically going to have 1/24 minus 1/30. That's our combined rate. And if we multiply by the time, that's what we're looking for, that has to equal the job or the work, which is 1/2. And now we can do this math. So we'd have to, do a common denominator and then bring that over here and solve for t. And it's not that hard if you know how to work with fractions, but a lot of people don't like working with fractions. So what I say is get rid of the fractions, right? And what our book tells us is we can give a value to these things. We can get rid of fractions, right, by multiplying by one number, 120. But I told you guys you can get rid of fractions by multiplying by each of the denominators. And we could have done that. We could have multiplied everything through by 30. Then we could have come by and multiplied everything through by 24. And then we just would have had to reduce at the end. It would have been the exact same thing as multiplying by 120. 120 just happens to be the least common denominator of 24 and 30. But that also brings up another thing is when we talk about a rate as being 1/24th, instead of that, we can actually think of a rate as being a number of things, right? So our job was filling one pool. And if it takes 24 hours to fill that one pool, then we're doing 1/24th per hour, right? But if instead we thought of that pool as being 120 gallons, then it takes 24 hours to fill 120 gallons, right? So 120 gallons, that's our work, equals our rate, which is our time times our rate. Our time was 24 and our rate was R, that's what we're trying to solve for. And if we do this math, right, do 120 divided by 24, that was our time, right? That gives us our rate. And so now we do 120 gallons, right, in 24 hours. When you do that math, you get 5, basically, gallons per hour. So now the rate is 5 gallons per hour. And you're thinking, well, that's made up because we said it was 120. Yeah, it doesn't matter, it's 120 gallons. The math will always work. What I'm saying is we can make our rate whole numbers instead of fractions, because then the same thing happens for this thing, for draining, because it drains an entire pool. It drains all 120 gallons, right, in 30 hours. That's its rate. So you divide by 30 and you get 4. So its rate is 4. It's a -4, but it's a 4, right? So it basically drains 4 gallons per hour, while the other one fills 5 gallons per hour. So if they're working together, 5 minus 4, aren't you gaining 1 gallon per hour? You sure are, right? And so that makes the math a lot easier, because then we can go, all right, so they're doing 1 gallon per hour, and it's a 120 gallon pool, right? So it's going to take us 120 hours, but wait, remember that's for a whole pool. We don't need a whole pool, we need half of a pool, which is 60. So the answer is going to be, it's going to take them 60 hours. But again, that's not our final answer, because if they want to know how much total time, we have to add back that 12 minutes that we got from the beginning. All right, so have I thoroughly confused you? Yes, of course I have, probably. The bottom line is you can work with fractions and get these fractional rates, and then just get rid of the fractions by multiplying through. And that's probably the easiest thing to do. You can also always give your job a number value other than 1. And so instead of 1 divided by 24, it's a big number divided by 24, which will then give you a whole number for that rate, and then a whole number for the other rate. And so then when you combine those rates, it's again a whole number, and you're not dealing with fractions. But in either case, when you do the math, you can see that when we multiplied everything by 120, we got this same 5t and 4t. Remember, we had 5 and 4 from the other ones. And when you subtract that, you get t. And remember, we got 60 before. We got t equals 60. So it takes 60 hours to fill that pool, but there was those first 12 hours for the first half, and so it takes 72 total hours to fill the pool. Now, it all depends on the question. If they asked, how long does it take to fill the pool after the drain pipe is open, then your answer would have been 60. But if they asked for just how long does it take in total to fill the pool, then you would say 72. All right, does it make sense? Yeah, if we look back, 72 hours, 72 divided by 24 means that in 72 hours, remember the rate to fill was 24, so it would have filled 3 swimming pools. The rate to drain was 30. Because remember, it was filling for all 72. It was filling for the first 12, but it was only draining for the last 60. So in those last 60 hours, it was draining at 30, per. So that means in 60 hours, it would drain 2 pools. So we filled 3, we drained 2, and we're left with 1. 3 minus 2 equals 1. Yep, so that's kind of a simple way of looking back and seeing if the numbers make sense. And they do. Okay, the next type of problem we're going to look at is another kind of obscure problem. It's a very silly problem in the fact that you wouldn't really use it in the real world, like you'd use the problem of filling and emptying a pool in the real world. You just go turn the stupid drain off and then let it fill. But in any case, this one's even more kind of out there. But they do come up a lot. These age problems where they talk about some people and how they're related. This person is 5 years older than this person's twice as old as that person. In 10 years, they'll be 3 times as old, that type of thing, where there's always some people and some relationship between their ages. Then there's always a time shift. And then in that time shift, there's a new relationship between their ages. And sometimes there's even a second time shift and then a relationship with those ages as well. So here's a typical example. A man has a daughter and a son. The son is 3 years older than the daughter. In 1 year, the man will be 6 times as old as the daughter is now. And in 10 years, he'll be 14 years older than the combined ages of his children. What is the man's present age? Okay, so I read it all the way through and I understood the theme. The theme is they're talking about people's ages and they're moving in time. And I go, oh, it's one of those silly time shifting age problems. Okay. I also identified the question. What is the man's present age? So I can label that as my variable. That's my unknown, his age right here. And we can call it, M for man's age. Then I can go back and take it in bite-sized pieces and write everything down. So he's got a son and a daughter. The son is 3 years older than the daughter. I mean, if you just simply translate that, we'll put S for the son's age is 3 years older than the daughter. So that's daughter plus 3. So there's one equation there. Okay, in 1 year, the man will be 6 times as old as the daughter is now. So in 1 year, right, this is his present age. Remember, M is his present age. So in 1 year, it'll be M plus 1. That'll be his age in 1 year. Well, will be, that's equals 6 times. So 6 times as old as the daughter is now. Oh, okay, so the daughter now, right, is just D. Not D plus 1, D, because it's how old the daughter is now, not how old the daughter will be then, right? And then it says, and in 10 years, he will be, okay, so now his age plus 10 will be, that's another equals, 14 years older than, okay, so plus 14 to something, 14 years older than what? The combined ages of his children. Okay, so let's read that. It's the combined ages of his children when? In 10 years, he will be 14 years older than the combined ages of his children. Do you notice how it doesn't say the combined ages of his children now? So those ages are his children's ages also in 10 years. So he'll be 14 years older than the combined ages of his children, which is going to be son plus 14, because that's how old he is in 14 years, plus daughter. Oh, sorry, not plus 14, dummy, plus 10, because it's 10 years from now, right? So it's son plus 10 and daughter plus 10. And then, of course, the 14 more. So let's clean that up. His age plus 10 is going to be son plus daughter plus 10, 20, 34. And then we can even move the 10 over and go, his age is son plus daughter plus 24. We also have his age plus 1 is 6 times the daughter's age, or his age is 6 times the daughter's age minus 1. We also have the son equals the daughter's age plus 3. So there's all of our quote-unquote hidden equations, right? We have a bunch of them, but it's basically this one, and this one. Okay, how many unknowns do we have? We have 3. We don't know his age, the son's age, the daughter's age, right? M, S, and D are all unknowns. And luckily, we have 3 equations because the rule is you can only solve for the number of variables if you have that many equations or more, right? So I've got 3 unknowns. I have 3 equations. I can solve it. Well, our goal is to get one equation with one unknown. So we want one equation with all the same letter. We want a bunch of M's, a bunch of S's, or a bunch of D's. It doesn't matter which, but we just want a bunch of the same letter. So ask yourself, can I start doing some substitution, right? Are there equations that simply relate one variable to another? Well, yeah, I've got M related to D, and I've got S related to D. Hey, I've got 2 different variables that are both related to D, so I can substitute both those in. So if I go up here and I have M equals S plus D plus 24, by substitution, M is just 6D minus 1, right? And then instead of S, I can put D plus 3, and then plus D plus 24. And look at, we now have an equation with nothing but one variable. So clean it up, right? 6D minus 1 equals 2D plus 27. So we combined like terms on both sides of the equation. Now we're going to isolate our variable. We're going to bring the 2 over here so it keeps everything positive. We're going to have 4D minus 1 equals 27. Bring the 1 over there. 4D equals 28. Divide by 4. D equals 7. And remember, D is the age of the daughter now. But we want to know what's the man's present age. So, okay, well, over here, we have this equation here that says the man, his age, right, is 6 times the daughter's minus 1, right? Because it really was in 1 year he will be 6 times, right? So when we do this, if we plug in the 7, 6 times 7 is 42. 42 minus 1 is 41. And the man's age is 41. Of course, if we need to know the son's age, right, over here, the son is 10. And now we could double check all of our math and make sure it makes sense, right? In 1 year, he'll be 6 times as old as daughter is now. Well, at 42 is 6 times 7. In 10 years, he'll be 14 years older than their combined ages. Well, in 10 years, he'll be 51. She'll be 20, and the boy will be 17. So 20 and 17 is 37. 37 plus 14, right, is 51, which of course would be his age plus 10. So everything works. Yay, we're done. Okay, now here's how we would solve it using the kind of more generic book way of you can write down their ages now, their ages in 1 year, their ages in 10 year. Again, you could just use MD and S instead of man's age now and daughter's age now and son's age now, but it's a good way to kind of organize your thoughts. You also know that we don't need all those, right? We didn't use everything plus 1 and everything plus 10. We just noticed that there was 2 different time shifts, and so those were the ages at all of those time shifts in case we had to use some of them. The first equation, right? The son was equal to the daughter's age plus 3. Then we had that man's age now plus 1, right? So in 1 year, he'll be 6 times as old as she was. We solved that for the man's age. Then they told us in 10 years, it's the same thing as 14 plus the kids' ages also in 10 years. That gives us our third equation. And then we figured out that, hey, by substitution, we can start plugging these things in and get everything in terms of the daughter's age. Do a little algebra, see how now they finally put in D's instead of daughter's age now. Do a little math and get the same thing we did. Her age is 7. Plug that back into what they told us and go, his age now is 41. Okay? We can look back and double check everything, which we already did. And so my point is that if you just have some basic math skills of being able to translate English into math, being able to systematically write down everything they tell you, and then look for that hidden equation, you can solve even these odd things. All right, here's our last example, and this one's really weird, but it's a good thought process. You know, there's not a lot of math in this thing, but it's a lot of thinking, which is a good skill to have. The number of pages of a bulky volume, i.e. a book with a lot of pages, right? To number all of those pages, the printer used 4,001 digits. Now, first of all, you got to understand what the heck they mean by that. So let's say you had 5 pages, then pages 1, 2, 3, 4, and 5. That would have taken 5 digits because there's 1 digit in 1, 1 digit in 2, 1 digit in 3, right? 1 and 4, 1 and 5. Once you get to 10, you need 2 digits, right? 11 is 2 digits, 27 is 2 digits, 98 is 2 digits, right? So that's what they mean by 4,001 digits. It's basically how many total little symbols that you have to use for all of the page numbers. It was estimated that the volume has about 1,000 pages. Is this a good estimate or not? And then how many actual pages does it have? Okay, so let's do some thinking about this, right? Let's understand the question. Page 1 uses 1 digit, page 49 uses 2 digits, right? Page 125 uses 3 digits, page 1027 would equal 4 digits, and so on and so forth. So when we see that pattern, we can start to figure out ways to add up some things. If the book only had 9 pages, because those are all of our single digit pages, how many digits would it have? If the book had exactly 99 numbered pages, so because 10 through 99 are all 2-digit numbers, then can we add up how many digits that is? And so on. So that kind of goes back to Polya's idea of solving for a simpler equation. If we can solve these simpler ideas, we can solve for the bigger one. If we know how many 9 total numbers are, right? Single digit pages are the first 9 numbers, and that's easy. That's just 9 digits. Then we do the double digit pages. Well, how many double digit pages are there? There's all the pages that are numbered 10 through 99. If you do 99 minus 10, that gives you 89, but you have to actually add 1 back in because think about it this way. If you go from 10 to 11, that's 2 pages, right? But 11 minus 10 is only 1. So you always have to add 1 back to get the number of things. So 99 minus 10 is 89, add 1 back. There are 90 pages that go from 10 to 99, which makes sense because we have 9 pages that go from 1 to 9. And there are 99 total pages. So if we take those 9 away, we know there are 90 other pages, right? So there are 90 pages that are numbered 10 through 99. So each of those pages has 2 digits. So 2 digits times 90, there's 180 digits to do all those pages. Okay, let's expand the pattern. Now let's look at all of the pages with 3 digits. So that's 100 up through 999. Well, again, up to 999 is 999 pages, but we already have the first 9 pages are single digits. Then we have 90 pages that are double digits, so those 99 pages are gone, and that leaves us with the other 900 pages. 900 pages all have 3 digits, right? 100 up to 999. So 3 times 900, 2,700. So if we add those 3 numbers together, we already have 2,889 digits. That just gets us up to page 999. We're looking for 4,001 digits, so we need more. Well, if we had all of the 4-digit pages, then that would be there are 9,000 more, because that would take us up to 9,999, but we've already accounted for the first 999, so that'd be 9,000 more pages at 4 digits each. That'd be 36,000 digits. That would be way above the 4,001 that we need. So we know the answer is somewhere in the thousands, but not way up there, right? So it's going to be closer, right? Closer to 1,000. Well, we already know that 1,000 wasn't a great guess, because 1,000 got us right here, basically at 2,889. That's 999 pages. That 1,000th page would be 3 more digits. So that'd be 2,892. So it's not terrible, but it's not great as a guess. But we can actually figure out how many of those 3-digit pages do we have. Sorry, 4-digit pages, right? Because we have 1,000 and above, so that's 4 digits, 1 and 3 zeros. So we need to figure out how many of those are. Well, it's going to be 4 times something minus 999 is going to be what we've got, because that's the total pages minus the 999 that we already did, right? So let's say if it went up to the page 2,000. You would do 2,000 minus 999, and that would tell you how many 4-digit pages you have. Because pages 1 through 2,000 is 2,000 total pages, right? But the first 999 pages, we've already counted up how many digits those are, so we're looking for the remainder. So that's why the total number of 4-digit pages is the total number of pages minus 999. So if we let x be the total number of pages, which is what we're looking for, remember, identify the question, then we take 999 away from it, multiply that by 4, and that will be the number of 4-digit pages times 4, and that will give us how many digits there are in those pages. So we can now solve all this, right? We've got 9 digits for the 1 single-digit pages. We've got 180 digits for all the 2-digit page numbers. Then we had the 2,700 for all the 3-digit, and then 4 times x minus 999 for all the 4-digit pages that we have. And when we add those all together, that has to be a total of 4,001. Whew! Do some simple math. Distribute the 4. Add the constants together. Then add those constants together again, right? We're combining like terms. Then we move that over so we can isolate our variable. Then we divide by 4, and we get 1,277. Remember, x represented the total number of pages. So the book has 1,277 pages. Now, I know this one might have thrown you for a loop, and this one is, more of a thought experiment than a math experiment. Really, the only math that we did was this last little bit of solving for x. But, you would never get here without kind of seeing the pattern of there are 9 single digits, then 90 double digits, then 900 triple digits, then 9,000 4 digits, and so on and so forth, and taking each of those and multiplying, right? So 90 times 2, 900 times 3, 9,000 times 4, and then figuring out, okay, what's the overlap? If we don't have all of the 4-digit numbers, or we don't want to do all 9,000 of them, then where do we stop? Well, if whatever our page number is, if we subtract 999 from it, that will give us how many overlap there are above and beyond 999. And that will be just those 4-digit numbers, right? Because after 999 comes 1,000, which has 4 digits. And then from there, you can solve for the page number. I hope it made sense, guys, but don't panic if this one didn't make sense. The bottom line is, do you understand the 4 steps? Can you go through the basic 4 steps of Polya's stuff and solve basically any type of problem? That's what matters, not these specific ones. It's, can you do these generic 4 steps? Can you do my 4 steps? Can you draw pictures, identify your unknown, find the hidden equation, and solve something? That's what we're learning today, all right? And that's what you need to know to model various problems.